infrastructure that has joint servers, network servers, and gateways. And when it comes to building security, we can look at the building blocks of security. We have the end device, which is an important element of the overall architecture. And then we have the infrastructure, for which we do deploy infrastructure security. And in between, there is the wireless communication that goes over the air and also over the backhaul, most of the case over wired connections. And if we further dive into infrastructure security, looking at every element, we can talk about the perimeter security, which involves making sure only authorized endpoints can be communicating with whether it's a gateway or the network server, etc. And then when running software on the platform or accessing the data, how we ensure the integrity of the data, and that's what we call platform security. And again, among all these network infrastructure elements, we still have to deal with communication security. And when it comes to wireless communication, given that we cannot rely on physical security, what we do is we rely on cryptographic security, which needs to ensure mutual endpoint authentication, data origin authentication, integrity and replay protection, and encryption. And that's all using a strong cryptography. So in our standard, it all starts with having a long-term trust and shared credentials shared between the end device and the joint server, which gets used with a so-called joint procedure. This is a cryptographic handshake that performs mutual endpoint authentication to provide an ephemeral, to generate an ephemeral trust between the end device and the network server and the end device and the application server. And this ephemeral trust is also backed by ephemeral session credentials. And using that, we're able to provide, once again, data origin authentication, replay protection, integrity protection, and encryption for the LoRaWAN traffic that runs between the end device and the application server. And these are all using strong AES-128 cryptography. Additionally, we also have this feature called firmware update over the air, FODA, which allows us to download large files to end devices, and even doing so across multiple devices at once, which is a very handy tool for updating the software on the end device. Just like you get updates on your iOS and Android phones, once in a while, hopefully less frequently, you would need to patch your devices maybe with some new features or maybe with some software bugs at the application layer. And for that, we provide a FOTA feature. That's one of the standards that we have published in the technical committee. And that is your insurance for anything that you may discover after the devices are deployed in the field, and you can run FOTA over the LoRaWAN connectivity. So in the remaining part of our session, we will be going over every one of these network elements, the end device, the joint server, the network server gateway, and the application server. And for that, I'd like to now turn it over to my colleague, Martin, who will be covering the end device part. Martin.
Thank you, Arthur. So, I'm Martin Wittrich from Semtech, Switzerland, where I lead a group of embedded software engineers, mainly working on the firmware running on the LoRa transceivers and bringing life to them. So, let's go into some aspects of the end device security. First of all, what are the main tasks of an end device? The end device should, of course, be able to authenticate himself on the network and then be able to transport end-to-end encrypted data. But apart from that, it also has to ensure the integrity of its functionality and so ensure the integrity of the data which is transmitted. This will, of course, require some security, namely protection of keys during the whole product lifetime and some cryptographic algorithms which are using these keys and, of course, protect its software running on the end device to ensure the integrity of its functionality. To illustrate this, we'll take an example of a Semtech LoRa Edge platform from the LR11XX family, embedding some interesting security features. It contains pre-injected keys and EUDIs during the chip manufacturing in a secure production environment and the secure on-chip storage with a crypto engine which is optimized for LoRaWAN operations, and the secure boot to protect the integrity of its firmware which is also available with an embedded LoRaWAN stack. So, to initiate a LoRaWAN session, the device will build a join request message using his stored root keys and AUIs and send it to the join server. The message integrity code, called MIC, of the join request will allow the join server to authenticate the device. Hopefully, the device will then receive back a join accept message, which it will be able to decrypt and check the authenticity with the same root keys. Based on the information in this exchange, it will be able to derive locally its session keys, and note that there are no key exchange over the air during this join procedure. The device will then have two open secure channels, one to the network server for all MAC-related operations, and one to the application server for application-specific data transmission and reception. So, as already mentioned, the keys have to be protected during the whole lifetime of the product, which indeed starts during the provisioning of the keys and the AUIs before the device is even deployed into the field. Keys and AUIs are generated on a secure server or HSM and transferred into the device through a secure local channel or in a secured production environment. This provisioning data is then stored into a specific part of the device called crypto engine here. The name of this part can vary, like Crypto Island, Crypto Engine, or Secure Element for high-end devices. It contains persistent memory for root key storage and volatile memory for derived session keys, and an AES engine to perform the cryptographic operations, usually using some hardware accelerators for best performances. This crypto engine is designed like an island inside the device, with very limited access from the outside through a dedicated API, allowing the needed cryptographic operations like the AES encryption, decryption, MIC calculations and verifications, as well as key derivation or writing new root keys if needed. But what it does not allow is to read out the keys from the device. All the key access management is done on the cloud side. Usually, these crypto engines have some countermeasures implemented against physical or side channel attacks to mitigate the risk of leakage of the root keys. So now, to protect the integrity of the whole platform, including its functionality and the transmitted data, it has to be ensured that the software which is running on the end device is the one provided by the device manufacturer or an authorized one. To do that, the state of the art is to implement a secure boot. A secure boot is a process ensuring that the device will boot on an immutable source code first, typically located in some ROM memory. This bootloader is then able to authenticate the software to be run on the device, which is usually located in some flash memory and can be updated locally or over the air. For this, during the build of the software, the build server will ask to sign the binary with a digital signature. The signature is computed in an HSM or on a secured server with a private key, and then appended to the binary. The whole is flashed into the device. The bootloader will so be able to verify the signature with its public key and authenticate the software as a software coming from the trusted source. If this fails, the software will not be launched. This is the base of a root of trust. This mechanism will protect the device against malicious software which may alter its functionality, the integrity of its data, or even for somehow somebody trying to attack against the device itself or even against the network. A similar principle with authenticated fragments can of course be applied on some fragments for a partial update over the air through the LoRaWAN network. So, to summarize, I talked about three aspects of the security of the end device. The first one is a secure injection of keys and e-wires into the device during production, the secure storage and usage of these keys, and the protection of the integrity of its software. Now I will hand over to Rames, which will talk you through the joint server.
Thank you, Martin. So my name is Rames Saz. I am ThinkPark Product Manager at Activity. So Activity at a glance. Activity is a founding member of the LoRa Alliance with more than 40K gateways powered by ThinkPark and deployed by public LoRaWAN network operators in more than 50 countries. We also deliver enterprise private LoRaWAN networks that are deployed in more than 100 countries. And we also deliver location services through AppleWay trackers that are deployed worldwide and delivered with more than 200K units every year. So let's speak quickly about the joint server part of today's discussion. So one main question that many of us may have: should we really have a standalone joint server in the LoRaWAN architecture? What if we simply consider that we can co-locate the joint server function with a network server in one combined server? So to answer this question, let me take you through the journey that the root key of the device may take from the original key holder until it gets to the final device owner and gets commissioned in the server. And in this example, I will take you through the case where the device is made up of a secure element. So as you can see from this figure, the key may probably transit from the original key holder, which is a secure element manufacturer, then to the module manufacturer, then will be handed to the device manufacturer, and afterwards probably through intermediate actors like the distributor and the system integrator, before finally being under the possession of the device owner that will go provision that in the network server. So is that journey really secure? So the answer is no. And another thing to think about when we speak about whether it's good to have a standalone joint server or we probably need to combine the joint server with a network server is about a device manufacturer that would like to have a single way and a simple way to pre-commission their devices in a way that is generic, not really personalized for each network server provider, and yet have those devices activated away from home. That's what we call the roaming activation. So in this case, which joint UI should he set for those devices? So actually, the answer to both questions is the same. We need to have a secure, simple, and scalable way to have the original key holder pre-commission the root keys of the device in a way that is secure in a standalone joint server, and those keys to be securely stored, and then in return the key holder will get an owner token to be handed to the final device owner, probably printed on a QR code on a sticker on the device. And at this stage the device becomes generic, means that it has not been specifically personalized for a given network server, and yet it can be commissioned on any network server while the key roots of the device, the root keys of the devices remain securely stored by the original key holder. So let's take a global look at what it takes from end to end when we speak about the activation on a standalone joint server for which ThinkPark provides a service that is called ThinkPark Activation. So we have already spoken about the role of the device manufacturer that will go to provision their devices, what we call pre-commissioning. They will set the device's root keys in ThinkPark Activation services. They will get those keys securely stored with a hardware security module, HSM, and in return they will get an owner token that they would include with their QR code, so that at the end, the device owner, when they get access to the device, they will simply scan the QR code, and when they scan that, not only the device will be commissioned on the home network server of the device, but if this network server is also powered by ThinkPark, the ThinkPark network server will directly go claim the device's ownership on ThinkPark Activation service on behalf of the device owner. And at this stage, we are ready for step 3, which is the activation step that will be handled when the device is powered on and it sends its join request. Let's take a look at what happens with the join procedure here. So the end device will send a join request that will be routed to the join server through the network server, and then the join server in SYNCPACK activation is powered by an HSM to securely store the keys. The app key is known by SYNCPACK activation. It will do the key derivation, and at the end will generate the session keys, the network session keys that will be sent to the network server, and the application session key that will be wrapped by a key encryption key for sake of providing end-to-end confidentiality between the end device and the application server. This key encryption key, what we call here ASTK, can be only known by the joint server and the application server. And then we will see what happens later on when there is data flowing from the device to the application server. But just need to know that all the communication between the different network interfaces in SYNCPACK are completely secured by TLS. And then what happens when the device sends an uplink frame? It will be already encrypted by the application session key, and then the network server will receive this payload. It will deliver this payload as is to the application server, but on top of it, it will also send the application session key in an opaque format that will be wrapped through the famous ASTK, and only the application server will be in a position to use the known key wrapper, the ASTK, in order to deliver the payload by using the ASTK to decrypt the app ASCII and then use the app ASCII to decrypt the device's application payload. And here again, everything is secured by TLS. So let's wrap up. What are the key features of SYNCPACK activation? From security standpoint, we have the secure storage of the device keys thanks to the hardware security module powered by UT Macro Crypto Server SE series. And in this case, all the activation process, the activation code, is directly handled by the HSM so that the master keys will never leave the HSM itself. The second thing is that end-to-end data privacy is maintained for most stringent confidentiality applications that require end-to-end data to be encrypted between the device and the application server. And for those applications that would trust the network server to do the payload decryption and also the payload decoding, so they want the network server to do that on the application server, that's also something that is supported as a configurable option on SYNCPACK. The third thing is about the secure elements. So we are compatible with several secure elements: ST microelectronics, microchip, trusted objects, and IDEA. Sometimes we say, I like your security aspect, but traditionally we tend to say that security is not always the best or the most easy to use. But actually this is not the case here, because not only the solution is secure, but it's really low touch, because everything can be seamlessly configured and provisioned through QR codes. And for that, we invite you to visit Activity booth this afternoon, where we can show you how to simply and securely provision devices using QR codes. Last but not least, you can freely choose your deployment model, either through the SaaS option with redundant HSM cluster, or for fully on-premise deployment. And now let me hand over to Dave for the network server part of the discussion.
Thank you, Ramez. Yes, hello, my name is Dave Jundel. I'm the CTO of Senet, one of the founding members of the LoRa Alliance. Senet provides a core network platform service, an LNS plus OSS and BSS platform, and operates the largest public LoRaWAN network in the United States, as well as providing access to the Helium network worldwide, as we announced earlier. I'm going to talk to you, as Ramez said, about the network server component. So just a quick recap of the network server's functionality. The network server is the interconnect between the joint server, which Ramez just talked about, the application server, which we talked about at the end, and other network servers, potentially for those roaming use cases. It manages all of the link layer configurations and actions associated with the end devices. It assigns the device address to those devices. So in the LoRaWAN architecture, in a sense, the dev adder is like the IP address that you get assigned to your Ethernet card. The end device RF configuration is part of that as well, and usually the majority of the gateway configuration, at least as it's related to the functioning of LoRaWAN on that gateway. The network server is also able to monitor and adapt to all of the changing physical parameters in the network environment broadly, potentially even globally in many cases. So interference, changes in environmental factors, It allows some hybrid operations. So Ramez mentioned a key to this prior, where the network server may also be co-located with other functions. This is not always desired, but sometimes it is important. We have 2 use cases today in LoRaWAN where this is very often true, and that's supporting multicast and firmware updates over the air, which are both kind of intrinsically linked to how the network server operates. So that may change in future, but today those are often co-located. The operational and business support systems may also be part of a network server. So in the LoRa Alliance, we also talk about the LNS, and the LNS is really an engine that does these functions, does these LoRaWAN layer 2 functions. But because of its role in the network, it also is able to provide many other capabilities, things like network planning, network management, and device management, at least as it relates to the RF component as well. And so many network servers will also have these functions and capabilities. In addition to that, it also may provide alarms and alert systems that are useful as it comes to and it relates to security. So another simple diagram, you've seen many of these diagrams before. I think mine's the simplest, but not the most complete. I will give you that. So we're talking about the component that's connected to the gateways in the physical world. On the other side of the gateways are the end devices. And in the cloud or in the connected environment on the back end, we have the join servers, many of those, application servers, many of those that are ultimately connected to where the application presentation layers, the data is actually visualized, realized, and acted upon. When we talk about security specifically with the LNS, a lot of what is in the LoRaWAN standard is being talked about by my colleagues already here. So what we're going to focus on are the entities that are in addition to the LoRaWAN standard itself. So what are the things that are potentially, might be considered optional, but really are an important part of securing the LoRaWAN network server? So the first thing that we look at is we look at all of the external interfaces that the network server may present. And in the diagram we saw before, there really are at least 3, sometimes 4 key components to those external interfaces. So we have the connection to the gateways themselves. We have the connection potentially to external join servers, external application servers, and then finally we may also have interfaces to other network servers that may be connected to this primary one for roaming purposes. And again, this is becoming more and more common and important. So there's a few things that we want to be looking at. So one is we want to secure those interfaces. So even though the LoRaWAN transport itself is secure, and is secured from the end device through the gateway, through the network server to the application server, in any event, we still need to secure the communication paths between these devices. So there's several reasons for that. So one of them, obviously, at the gateway side, is that would be an ideal launching point for an attack. On the communication between the back-end components, we want to secure those as well because they are maybe the easiest point of attack from a certain perspective. So we're going to use, in most cases, a secure tunnel for that. TLS, IPsec, something along those lines. That's modern, that's up to date, that's well maintained. We want to make sure that includes both privacy as well as authentication and integrity. So that is both the ability of the network server to identify, prove its identity to the other end of that interface, as well as the other end of the interface to prove its identity back to the network server. So there are several ways of doing this. We won't go into the details, but certainly in most cases here, we're looking at a PKI solution, either both for server and possibly client authentication, or on the server side with some sort of shared key secret, a token, a key that's provided by the remote end to prove its identity. What's important about this, and we want to steer away from security solutions that are proprietary, that are closed, that are not public, is that we also want the ability to, when we've identified a breach of trust, to be able to revoke access to that entity. So that can be done through public certificates. It can also be done through the revocation of the tokens or the APIs that are used, API keys that are used to prove the identity of the remote end. Several of the folks here are also talking about the security components associated with provisioning the end device. We talked about that with the join server. It was talked about previously with the end device itself. So obviously these are key components of that. It's important that as that material is provisioned into the network server itself, that same level of security is maintained. So that's identifying to the network server the device, but the devices are uniquely identified, that they're given as a secure way of that information being presented to the network server initially, and that it is going to make sure that that information is then further segmented by the customer that owns that device within the network server. So one part of that that we want to talk about here is that segmentation of the data structures within the network server itself. So even though we may not be decrypting the data that is coming through the device, the network server is in a unique position to know an awful lot about the device, where it is, what gateways it's coming through, who the customer is that's associated with it. The network server may also be provisioned with additional metadata that is being provided as a convenience or a service to the end customer that may further describe information that might be deemed private, things like what the end customer is or what the actual geolocation of that device is. So all of these things can be considered confidential or susceptible to attack. So when the network server is provisioned and when it's storing this information, keeping it, it's important that that data is secured while it's in transit and secured while it's at rest, and that while it's at rest within the data, within the network server itself, that access to that data is regimented and strictly limited by the function of the entity that's accessing the network server. That is true whether that access is done through APIs, whether that's done from a network server to network server, joint server to network server, or through a non-standard API that the network server is presenting to a management platform, or whether that's simply the UIs that the network server itself is presenting to the end customers. The other thing that I want to mention is that the network server, due to its unique role in the network architecture and the architecture of LoRaWAN specifically, as a fundamentally centralized architecture, enables the network server to perform an important role in detecting and potentially mitigating attacks that are occurring. That central location within the architecture means that the network server is able to detect behaviors that may be indicative of attacks that are going on. So this is not necessarily talking about how to secure an interface, but really how to observe how interfaces may be being attacked. That can be a physical layer attack where a device has been cloned, is now representing itself someplace else in the network, a device that's supposed to be stationary that appears to be mobile, a device that's mobile that becomes very, very stationary. All of these sorts of things are flags that the network server alone really has the visibility to identify and potentially mitigate. So the mitigation may be somewhat challenging, but once you've identified if there's a clone of a device that's in presence, you can squelch one of those if you know which the right one to squelch is. In terms of how that data is being presented back to the end customer, obviously you can't do anything about it on the wireless side. We can look at replays of joint procedure. We can look at replays of end device messages, uplinks that are occurring. On the reverse side, from the northbound interface down southbound, we can look at duplication of downlink messages. It may indicate that there's a compromise on the cloud systems or the application servers, the joint servers that are present back there as well. On the network server to network server interface, the same thing is going to happen. Now we have certain key elements within the LoRaWAN backend specifications and the LoRaWAN layer 2 specifications that enable us to validate the trust levels between the network servers. But once we've detected that there's been a breach of trust that exceeds a certain allowable statistical percentage, that means we need to revoke trust from that entity. Again, it gets back to our previous slide where we talked about making sure that we are doing endpoint authentication as part of our API security. And finally, we want to be looking northward from the network server as well to identify layer 2, layer 3 indications that may represent that the entities connected to the network server have been compromised in a way that is unexpected. That can be changes in IP addresses, that can be the replication of data messages, the messages that are delivered with invalid CRCs or invalid checksums. All of those are indications that the network server is then able to take into account and present at the bare minimum warnings and alerts to the owners of those interfaces, of the owners of those devices, and in some cases even potentially identify what might be potentially mitigation steps. So for example, a compromised gateway that's disconnected from the network server and not allowed to connect again, the revocation of API keys, or tokens that allow a joint server to connect to the network server or an application server to connect to the network server. So that's the end of my presentation on the network server security. I would like to hand it over to Prasad to talk about gateway security. Thank you.
Great. Thank you, Dave. I'm Prasad Kantikanda, Vice President of Engineering at Multitech Systems. Briefly, Multitech, I think most of you might have used at some point our blue gateways that provide the LoRa connectivity. Multitech has been a leader in the wireless and cellular equipment manufacturing. A few things changed in the last few years for us. We were acquired by a company called SmartWave, who are specialized in vertical, application and hardware development, and also large-scale manufacturing facilities. And we also recently acquired another company called Radio Bridge, who are specialized in LoRaWAN sensors, combined with the sensor technology and the ability to manufacture at a large scale with our, 50-year-old experience in cellular, wireless, and LoRaWAN communication technology. Now we are in a much bigger position to do a quick end-to-end connected product solutions. So today my job here is to talk a little bit about the gateway security. And I know Dave and Ramiz and Martin, everybody talked about end devices, network servers, and joint servers, but ultimately you need a device to send all this data into the cloud. And our gateways, or the gateways that we manufacture, and many others actually do the job. So we're just going to touch a few points about the gateway security and what we want to do, and mostly as a common practices or recommended practices in general. And so the role of a gateway, gateways act as a conduit, right? Because they're really basically sitting in between the end device and the cloud, and then routing all the traffic to the network. Typically, they're running some kind of a packet forwarder software, listening to all the low-end devices, and then transporting the data into the cloud. They're mostly completely oblivious to all the key material, So no gateway stores any key material. The keys are at the end devices, and the other one is at the joint server. So you basically act as a pass-through to make sure the sessions are up and the data is going through. It is possible that some other gateways do store certificates and some other authentication material, basically for setting up a secure connection with the cloud servers. And typically the encrypted data just passes through the gateway. So what do we mean really by a gateway security here? The gateway security means the gateways are part of our enterprise networks, and we do not ever want the network to come down because of some kind of a security breach within the gateway. And the gateway should never be compromised by any external forces. We want to make sure that there is no way anybody can interfere with the data traffic or interfere with the device through any kind of external means. So the gateway should be rugged and reliable, and in an ideal world, the gateway should be able to detect any kind of a secure breach or some kind of a intervention, and then probably alert the administrator or send a notification. So these are some of the things that we want to ensure in the gateway, so that we could provide a reliable end-to-end LoRaWAN secure solution. So how do we achieve it? There are multiple things we can do. The three topics that I'm going to touch today are: one is how can we do it through the hardware design and the hardware process. The second thing is, of course, through the software mechanism, like what can we do in the software to ensure the container security, and finally, some kind of a physical security that we can do in order to ensure, the ultimate reliability of the system. Briefly going through the hardware security process, I think, everybody has mentioned of a secure boot, which has become almost like a standard to have in every gateway. So you want to have a root of trust, and then ensure you can boot through securely, and then at every stage validate the images and firmware so that the whole system is in a reliable state. And then wherever possible, use the TPM or some kind of a SAM within the hardware for securely storing any key material or any other authentication information that is required for connectivity. Hide any hardware interfaces that are easily accessible, so that nobody can tamper with the device once they're trying to do some kind of reverse engineering on hardware. And have good console, not provide any kind of a console access, and then have strong credentials. And if possible, you could send some kind of a network alert when somebody disconnects your Ethernet cable, or somebody plugs in a USB dongle which is unauthorized. So these are kind of the things that you could try to do in the hardware. From a software perspective, you want to ensure you are using a secure OS and the secure bootloader, and then, like I said, try to validate the firmware at each stage of the boot process. Implement file system encryption where possible, because not every hardware is capable of implementing file system encryption, because it's a little bit of burden on the system itself. It'll be good wherever you can do that. And more importantly, since the gateways are having a connection to joint server and app server and network server, try to maintain a good secure communication using either IPsec or TLS wherever possible. Use the highest level of encryption you can do, like AES 128 or of 256 if required. Implement access controls. I don't want to read through all these things, but these are some of the good practice that you can do in order to ensure a quality software implementation. And finally, just briefly touching on the physical security, wherever possible, try to put it in a lock and key, most secure mechanism. Nobody could break the lock. You don't know how it is, but, and ensure that you are fusing all the on-chip, whatever access controls are and the JTAG controls, so that, there is no other way of getting into the hardware. And wherever possible in the designs, do some kind of a resin or hide the traces where possible, so that your hardware is secure. So these are a few other things that you could do to ensure some quality on the hardware itself. And now I'll hand over to Hashim to talk on the application itself.
Thank you. My name is Hisham Dao. I'm a principal embedded engineer at Oxit. Oxit is an engineering services company, so we provide design services all from hardware design to firmware development, all the way to cloud and application development. During our years of experience, we have helped our customers deploy secure LoRaWAN solutions bundled with firmware over-the-air updates. I'm going to talk to you today about the application server. So far, we have seen that the device was able to join the network. It was able to encrypt the message and send it securely over LoRaWAN. The role of the application server when it's receiving a message is to decrypt this message and decrypt the message, decode it, and process it. The message before it's being received by the application server is still encrypted with the application session key, which was generated during the join procedure. The application session key is a 128-bit encryption key, and it's a symmetric key, so it's used to encrypt the message before it's sent by the end device. It's used by the application server to decrypt the message, and it's also used by the application server to send the message to the device. There are some, when dealing with the application server, there are some security needs that we need to keep in mind. The first one is after retrieving the key from the network, from the join server, we need to make sure that how do we store the key. We need to make sure that all the communication with the external server is done in a secure and an authenticated way. The application server is the only entity that is able to access unencrypted payloads from the end device. This makes it like a high level on the security chain. So we need to take security very importantly on the application server. So as I was saying, the application server needs to communicate with external entities. It needs to communicate with the join server in order to retrieve the application session key. It needs to communicate with the network server in order to send and receive messages to the device. No matter which protocol you are using, you can use MQTT, HTTP webhooks, or something else to do this, but no matter which protocol you are using, we need to make sure that this protocol is running on top of TLS. By enforcing a TLS connection, we are making sure that the channel between the application server and the external server is done in an encrypted and authenticated way. Because the application server is usually have like some custom logic running on it, usually the developers will need to have some sort of API to expose the data to an external application, whether it's a mobile application or a cloud application. Most of the times you also have some type of a server database where you need to store your data. This is the responsibility of the developer himself to make sure that this part of the network is secured, and as a minimum requirement, we recommend that you use TLS connection with any of the external servers. As the application server is a custom implementation, I'm going to go through some of the guidelines that you should keep in mind while deploying an application server solution. So the first thing to talk about, which is the application session key. After retrieving the application session key from the joint server, the application server needs to make sure to store this key in a secure way. So if you are using a cloud provider, I would recommend to use the management, like the key management service from your cloud provider. If you are using an on-premise server, I would recommend that you use a hardware encryption or hardware crypto engine that you can connect to your server, and this crypto engine, we can lock the keys in and then we cannot read it back, and all the encryption and decryption will be handled by the hardware crypto engine. If you are exposing an external API, make sure to install a firewall to close all the ports that you do not need on the server. Limit all the access to the server so that disable password login, and instead of password login, use key logins. And then the last thing that you should do is that when the message is received from the device, make sure to validate the message contents, and then make sure that only allowed characters are inside the message payload so that it doesn't influence your database storage. This is everything I want to talk about the application server, and I'm going to hand it back to Albert.
Thank you, Hisham. So, in summary, we provide end-to-end security with our technology as we've been standardizing in the technical committee. And on top of that, as our speakers explained, coupling that with good practice of implementation and deployment security, we're able to provide end-to-end full-stack security for the LoRaWAN deployments. And this has been built into our standard from the very beginning. If you go back to version 1.0, you will see it starts with all the bells and whistles of a proper wireless communication security facility. And we also support it in our certification, and together with the hardware level security provided by Secure Elements and HSM, we bring this to hardware level security as well. And supported by FOTA, we have the insurance of patching devices in the field in case problems emerge later. And that's why it's not really surprising to see that among all the gazillion of real-life deployments, we see several use cases that are using LoRaWAN in serving critical infrastructure, whether it's a smart city, smart lighting, tracking heavy machinery in construction sites, or tracking smart grid across the nation. LoRaWAN has been used, and people using LoRaWAN has the confidence that they have a reliable security thanks to the technology and the implementation and the deployment practices. With that, I'd like to leave you with a few more pointers and thank our speakers for covering the whole architecture end-to-end, not only the technology, but also touch upon the implementation, productization, and deployment practices. And thank you all for coming today. Thank you.